In section 11.9, we talk about mixtures of gases, and this will help us be able to finish that lab that we did last week. So according to kinetic molecular theory, each of the components in a mixture of gases acts like it's the only one there. And this is because kinetic molecular theory says that there are no interactions between the particles. So it doesn't really matter what the particles are. It's nitrogen or helium or xenon, whatever the gas particle is, it acts exactly the same. So the pressure for any individual gas in a mixture is called the partial pressure. The total pressure is the pressure of all the gases put together, and the partial pressure is the pressure of one of the gases. That partial pressure is related to how much of the gas is that individual gas, how much of the mixture. So the component's fractional composition times the total pressure will give you the partial pressure. We'll look at that. So the air in our atmosphere is about 90, there's no 90 anywhere in there, 78% nitrogen, 21% oxygen, 0.9% argon, and 0.04% carbon dioxide, and then traces of other gases. So the nitrogen molecules are the main component of the air, and so they exert most of the pressure. They're 78% of the mixture by composition, and then they exert 78% of the total pressure. The oxygen molecules are 21% in composition, and they exert 21% of the total pressure. So here looking at a different gas mixture, helium and neon. The fractional composition is the percent composition divided by 100. Because what does percent mean? Like 80%. That didn't work very well. Brand new stylus, and maybe it's not a very good one. This will be a fun day. 80%. What does percent mean? Per 100, right? So 80% is 80 parts per 100 parts. 80 divided by 100 is 0.80. This is what we call the fractional composition. It's just the percentage divided by 100. Or you can use it this way as well, 80 over 100. It's the same thing. So the partial pressure of a component is its fractional composition times the total pressure. So in that picture, it shows us that the total pressure is 1.0 atmospheres. And it gives us the partial pressures of each individual gas, and it gives us the percent composition. Let's calculate the partial pressure and see if it's correct. So for helium, the percent composition is 80%. So to find the partial pressure for helium, we're going to take 80% as a fractional composition and multiply by the total pressure, and we get 0.80 atmospheres. That equals the partial pressure for the helium. We can do that for the neon as well. Let's do it a slightly different way and show you that this other way works too. 20% neon. That means there's 20 per 100 for the neon times the total pressure. 20 over 100 is 0.2 times 1 is 0.20 atmospheres. And that equals the pressure of the neon. So if we know the partial pressures of the gases and the total pressure, we can calculate the percent composition. Or if we know the percent composition, we can calculate the total pressure, we can calculate the partial pressure. So there's three different quantities going on here: total pressure, partial pressures, and percent composition. And if we know two, we can calculate the third. Any questions? Let's do an example. A gas mixture contains 64% methane and 36% ethane. If the total pressure is 1.44 atmospheres, what are the partial pressures of each component? So we're going to do the same calculation we just did on the previous slide. So for the methane, its percent composition is 64%, so its fractional composition is what? It's 0.64, right? Or 64 over 100. We're going to multiply that by the total pressure, which in this situation is not 1, it's 1.44. So 0.64 times 1.44 equals 0.9216, 0.92 atmospheres. Each of these, well, the first number, the percent composition has two significant figures. The total pressure has 3. So the composition limits our answer to 2 sig figs. For the other one, ethane has a percent composition of 36%. So 0.36 times 1.44. We're essentially taking 36% of the total pressure. 0.36 times 1.44, we get 0.52 atmospheres. Now, as kind of a check, you should be able to add those up and come up with the total pressure. You might get a little variation in that uncertain digit, but it should be really close. If it's not, then you did something wrong. Any questions? So those sorts of calculations are good to know, but they're not essential. What we're going to talk about right now is the more important type of partial pressure calculations. So a guy named Dalton studied mixtures of gases, and he came up with a law. Remember, a law says what happens. It says if you do this, this is going to happen. Here's a relationship, but it doesn't explain why. Dalton's law of partial pressure says that the total pressure of a gas mixture is equal to the partial pressures of each gas added up together. So this is the law right here. And it goes ... because it's true for however many gases. If you have a mixture of 2 gases, or if you have 150 different gases, you just take the partial pressures and you add them up. So for 1 atmosphere of air, which is normal atmospheric pressure, the total pressure, I just realized there's a mistake in that slide, isn't there? The total pressure equals, that shouldn't be there, the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of the argon. We can do that a little better. Make it disappear a little bit more. My class yesterday didn't catch that, and I didn't catch it yesterday either. The total pressure is the pressure of each individual gas. We calculated those from the percent composition in a previous slide. So 78% nitrogen, 78% of 1 is 0.78 atmospheres. So that's the pressure of the nitrogen right there. Here's the nitrogen. Here's the oxygen was 21%. So out of 1 atmosphere, 0.21 atmospheres are from the oxygen. The argon was, I believe, 1%, and then the rest of them are so small that they don't matter because our total, our uncertainty lies in the hundredths place, and everything else is smaller than that, so we don't even have to consider it. But we add all these up together, and we get 1 atmosphere. Does that make any sense? It's a little bit like, you got people in an elevator. You got 5 people in an elevator. What's the total mass? Well, it's the mass of each person added up, right? So it's the pressure of each gas added up together. So then we can do calculations like this. A sample of hydrogen gas is mixed with water vapor. So what we have here is we've got hydrogen gas and water vapor, water in the gas state. So we have two gases. The mixture has a total pressure of 745 torr. The water vapor has a partial pressure of 24 torr. What's the partial pressure of the hydrogen gas? Well, Dalton's law of partial pressures tells us that the total pressure equals the pressure of the hydrogen plus the pressure of the water. So if we rearrange this equation, we get the pressure of the hydrogen gas must equal the pressure of the total gas, the total pressure, minus the pressure of the water. Well, they gave us the total pressure, is 745. They gave us the pressure of the water. So the pressure of the hydrogen equals the total pressure of 745 torr minus the pressure of the water vapor, 24 torr. And that's what, 721. Did I do that right? So the hydrogen is exerting 721 torr of pressure. The water is 24 torr, and so altogether that adds up to 745. This kind of math sometimes trips people up because it maybe seems a little too easy. It is just that easy. You know, if I have 5 cookies and I give 2 to Johnny, how many cookies do I have left? That's what this is doing. Okay? So don't try to make it complicated. Think about, cookies or something, unless it makes you hungry. Any questions about this sort of an example? This is the kind of calculation we need to finish that lab we did last week with the hydrogen gas. This mixture of gases business actually has impact on real life experiences. So air at normal atmospheric pressure has a partial pressure of oxygen equal to 0.21 atmospheres. If you go up into the mountains, yeah, there went my wireless universe. Didn't hit the floor though. Okay, stay. We're privileged here to live very close to Kings Canyon National Park. Hopefully all of you have been up there at least once. It's beautiful up there. But it's high elevation, right? 6,000, 7,000 feet. The air is a little thinner up there. And so if you run around or if you go on a hike, you're like, man, I'm getting winded so fast. What's going on? The air is, we say it's thinner, right? There's less atmosphere up there. The atmospheric pressure is less than 1 atmosphere. And so the amount of oxygen that's available to you in that air is also less. And so that's why you get out of breath at higher elevations. The partial pressure of oxygen decreases. The composition of the air is the same. It's still 21% oxygen. But the total pressure is not 1 atmosphere. So at higher elevations, the total pressure decreases, and so does the partial pressure of the oxygen. So if you're going to go really high, like if you're going to hike Mount Everest or something crazy like that, I don't know why people do that, but they do. You need to take oxygen with you because there's just not enough up there for you to breathe. In an airplane where they fly above the highest mountains, they have to pressurize the cabin because otherwise everybody would pass out from lack of oxygen. It's called hypoxia, oxygen starvation. And when you get to a severe case of that, at less than 0.1 atmospheres of oxygen, you're going to lose consciousness and you could very well die. Because we need oxygen, right? And you just cannot breathe enough to get that oxygen in at very low partial pressures. So this table, well, I guess it's not really a table, it's a graph. This shows here if this is air at the surface of the Earth, and then if we get partial pressures, this is oxygen partial pressures here, if we get less Much less than this, we start to feel the effects of that, and when we get down to really low amounts, we get into trouble. But too much oxygen is also not very good. And this can happen when you're scuba diving. Personally, I don't do that, but some people do. So too little oxygen is bad for you, too much oxygen is also bad for you, oxygen toxicity. And this is the case with anything I can think of in terms of a physical substance. Too much water is bad for you, but not enough water is bad for you. And so, people get all freaked out about toxic chemicals. Well, everything's toxic at some level, okay? So you just have to be in the right range. So oxygen toxicity happens when the pressure gets above about 1.4 atmospheres. Symptoms of that include twitching, tunnel vision, where you lose your peripheral vision, you can only see in the middle, convulsions. So as you can imagine, that would not be a good thing to experience when you're far under the water, right? All of a sudden in trouble, you can't see, you're having convulsions, you're not going to be able to swim up to the surface or call for help. It's bad. So let's look at this illustration here. At the surface, the pressure of the air is 1 atmosphere, and so the pressure of oxygen is 0.21 atmospheres, the partial pressure. When you go deep into the water, 30 meters, you have to take pressurized air with you, because now the pressure of the water pressing in on you, if you don't have pressurized air, your lungs aren't going to be able to expand. If you just had air at normal atmospheric pressure, like maybe you had a giant straw going down. Did you guys ever watch the Flintstones? Remember there was this one episode where they're hiding in the swamp and they've got these straws. A snorkel works when you're close to the surface, but an extra long snorkel won't work, because as you go down in the water is pressing on you more than our atmosphere does, and you won't be able to expand your lungs to breathe the air. So you need pressurized air. So down at about 30 meters, you need a pressure of 4 atmospheres to be able to breathe. Well, if you're breathing compressed air, now the partial pressure of the oxygen is 0.84 atmospheres. So you're getting a lot more oxygen. If you continue to go down, the pressure regulator on the scuba equipment controls that pressure for you. And that's why they make you take all those classes before you can get certified, is because it's a lot more complicated than just breathing into a thing. So you go down farther, the oxygen partial pressure is going to go up and up and up. And so that's not a good thing. Nitrogen can be dangerous too. Let's go back here real quick. So here's the partial pressure of nitrogen then at 30 meters is 3.12 atmospheres. That's a lot of nitrogen. Well, you can get into what's called nitrogen narcosis. It's also called rapture of the deep. Apparently it feels similar to being slightly drunk or tipsy. And so, as you can imagine, being drunk far under the water is not a good idea either. So to avoid something like that, deep sea divers, and that's defined as being 50 meters, all this stuff is just kind of for your information. I'm not going to quiz you on this. They use special mixtures of gases. One of them is called heliox, and that's a mixture of helium and oxygen. Helium does not have this effect on us that nitrogen does when we get too much of it. And so basically we're using helium to dilute the oxygen so that we don't get too much oxygen when we're breathing this highly pressurized gas. Of course, if you could hear yourself talking underwater, do you know what helium does to you? It makes your voice sound really funny because it has a different density than the air, and so it makes your vocal cords vibrate differently and makes you sound like Mickey Mouse. So we could do calculations for this. A diver breathing heliox with an oxygen composition of 5%, the air's 21%, heliox is 5%, wants to adjust the total pressure so that he's getting the regular partial pressure of oxygen, or 0.21 atmospheres. What total pressure does that heliox need to be? Well, how do we approach this? The total pressure, well, that's not what I wanted to do. The pressure of the oxygen, way back when we first started talking about this stuff, the pressure of the oxygen equals the fractional composition, which they didn't introduce this to you. This is the fractional composition. I just didn't want to write all that out in the equation because it's too long. That's why we use variables. The fractional composition times the total pressure. So the fractional composition of this heliox is 5%, 5 over 100, or 0.05. We want to find out what the total pressure is. So we need to rearrange the equation, and we'll do that by dividing both sides by the fractional composition. We rearrange that equation, and we get the total pressure is equal to the desired partial pressure of oxygen divided by the fractional composition of the oxygen. The partial pressure of the oxygen that we want is 0.21 atmospheres. And the fractional composition of the gas is 0.05. That's not 0.05, 0.5. So we get 0.21 divided by 0.05 equals 4.2. So if you're breathing heliox underwater and you want to have the right amount of oxygen, you need to have the total pressure of that gas be 4.2 atmospheres. So this is a good sort of calculation to understand. This is not critical. Okay, so if you don't get this, you still pass the class. If you want to get an A on the test, maybe you should understand this one. This section kind of is jumping back and forth. So we did something not so important, and then we did something important and not so important. Now this is important again, collecting gases over water. This is what we did in lab. We generated hydrogen gas, and we collected it through water or over water. So this is a slightly different arrangement than what we had, but you can have we did magnesium and hydrochloric acid, but we reacted it right in the container that we were collecting the gas in. But you could also have it in a separate container with a tube going into an inverted container full of water. And as this gas is generated, it's trying to escape, and it will bubble up through the tube and displace the water. So above the water now, we have the hydrogen gas that was generated, but we also have water vapor. Because when water sits, it starts to evaporate. So the water in here is evaporating a little bit. It's going into the gas state. And so there are water molecules in the gas state here mixed in with our hydrogen. So if we wanted to know the pressure of the hydrogen, but there's also water in there. So the pressure of the water, turns out, is only dependent on the temperature of the situation. So the warmer the water, the faster it evaporates, the more gas molecules you have here. It's going to reach a state where it's not going to continuously increase until all the water molecules evaporate. And if you're interested about that, I'll explain it to you during lab. We'll also talk about that in another chapter. But the partial pressure of the water above the water surface here is going to be dependent on the temperature at which we collected that gas. So the total pressure up here is going to equal the hydrogen pressure plus the water vapor. And so how do we know what the vapor pressure of the water is? Well, we just look it up in a table because it depends on the temperature. And so they've done studies, and they figured it all out, and they put it in a table, and there you go. So here's an example. Hydrogen gas was collected over water. The total pressure was 758 millimeters of mercury. The temperature was 25 degrees Celsius. What's the partial pressure of the hydrogen? Well, this is Dalton's law of partial pressures. The total pressure equals the pressure from the hydrogen plus the pressure from the water. Those are the two gases that are present. We want to know the pressure of the hydrogen gas. So we'll rearrange this equation. The pressure of the hydrogen gas equals the total pressure minus the pressure of the water. Because if I have 5 cookies and I give 2 to Susie, how many do I have left? 3, right? How do you just do that in your head? Well, you take 5 minus 3 because I had 5 and we took away 2. What's left? So there's the total pressure, and if some of it is from the water, how much is from the hydrogen? Well, you just subtract them. So how do we find out this partial pressure of the water? We look in the table. The temperature is 25 degrees. And so we find that in our table. So 25 degrees Celsius, the partial pressure of water is 23.8 millimeters of mercury. So the pressure of the hydrogen is going to be the total pressure, which we were told is 758 millimeters of mercury. I'm going to write it down here because I'm going to run out of room. And we're subtracting the pressure of the water, which we look up in the table. It's 23.8 millimeters of mercury. And the calculator will tell us 758 minus 23.8. The calculator will tell us 734.2. 734.2. But what should we round that to? So a little review of significant figures here. Where's the uncertainty in 758? It's in the last digit, right? That's in the ones place. In this one, the partial pressure of water, it's in the tenths place. But the ones place is a greater uncertainty, and so our answer has uncertainty in the ones place. So we're going to give this answer as 734 millimeters of mercury. Okay? So you need to do that calculation with your gas from the lab we did, because we know the total pressure, it was the outside pressure, and we knew the temperature of the gas, so you can find the partial pressure of water, and that allows you to find the partial pressure of the hydrogen gas.